All right, this is a classic physics problem that involves a roller coaster. So we have a roller coaster here. Let's say it starts with a little bit of velocity, and then it goes down the hill and up to B and then to C. And what we're going to do is we're going to analyze motion, and this time in terms of energy, work, and potential energy at any of these spots. The entire idea is that the total energy here should equal the total energy there, should equal the total energy there, just because of conservation of energy. Now that's true if we're ignoring friction. We'll deal with friction later. But if there's no friction, then whatever gravitational potential energy I start with here should start getting converted to kinetic energy as I go down. Less potential, more kinetic, less potential, more kinetic. And then when I get to the bottom, assuming I assign h equals 0 over here when I'm at the bottom, here, all of the gravitational potential here and kinetic, if I started with it, will all be 100% kinetic down here. Then as I go back up, more of the energy goes into potential, less into kinetic, and then I get to the top here, I got a sort of combination of kinetic and potential, because I'll still be moving pretty good. But all along here, every spot along the way, the total, so if I start with 100 joules here, the total energy is 100 joules, 100 joules, 100 joules. It's just changing form, all right? So if we understand that, we understand the equations that come into play. So I'm allowed to say that the total energy at point A of the system should equal the total energy at point B, should equal the total energy at point C, or I could put an infinite number of points along the way. So the only question then really is to think about what types of energy we have at different places. So what do we have at A? I said that it started with some gravitational potential energy as well as that it's moving. So that means at point A we would have a little bit of energy due to motion, 1/2 mv squared at A. That's the kinetic energy it has. It's going to have some gravitational potential energy equal to mgh1, and that would be it. By the time we get to B, it will have a different amount of kinetic energy. It's going to be more, plus a different amount of gravitational potential energy. And rearrange there. At point C then we'll have 100%, at this point right here, it should be 100% kinetic energy just like it should be here because we define h equals 0 at here. Remember that's a relative thing. We could define h equals 0 anywhere we want to. So I'm going to say h equals 0 at C, which means by the time we get to C there'll be no kinetic, mgh will be 0 and it will all be kinetic energy, 1/2 mv. Oops. There. It'll all be kinetic energy, 1/2 mv c squared. All right. This basic idea is basically the law of the conservation of energy. We're just saying the total energy, if I have $100 here, $100 here, $100 here, all that's happening is it's changing forms at different points. And this really basically allows you to fundamentally solve lots of different types of problems. It could be a problem where we're just rolling down a hill like this, ball. Same idea, it's gaining kinetic energy and losing potential energy and so on. Now, what if we include friction into this system? Is it still going to be true that energy at A equals the energy at B equals the energy at C? It will not be true because as I go from each point, friction is acting, so I'm losing energy due to friction, losing energy. The entire way I'm losing mechanical energy from the system. Gravitational potential energy and kinetic energy are considered mechanical forms of energy. So that means that the energy at B is less than A, and the energy at C is less than B because of the dirty work done by friction. So it's constantly taking energy out of the system, basically in the form of heat. So what happens is, as we have friction work, it's doing negative work, because the force of friction is in this direction, opposing the motion of the roller coaster. So it's doing negative work the entire way, which takes energy out of the system. The way we would deal with that quantitatively is we would say that the energy at A minus energy lost due to friction, and energy lost due to friction is going to be the negative work due to friction. So that would be the force of friction, let's say from here to there, all along the way. We'll call that distance d. And the force of friction is acting over that distance. So whatever energy I start with minus energy lost due to friction should equal the energy left over at B. Okay? I could do the same thing with comparing B to C. Or from A to C. For example, I could say the energy at A minus the frictional loss to B minus the additional friction loss from B to C, we'll call that D prime, which would be that distance there, should be equal to the energy I have left over at C.